In our last week here with gas laws, we'll be taking a look at the kinetic molecular theory. Most of this is conceptual in nature with how gases, at least we think gases, actually behave. So far, we've covered all the gas laws, but the gas laws are actually a result of the kinetic molecular theory. So, this happens to be a model that helps our understanding for what happens to a gas as they undergo different environmental changes. Gases themselves are very large number of molecules that are in continuous random motion. And they also experiencing elastic collisions, perfect collisions that prevent them from slowing down or losing energy. Now, the combined volume of a gas is really negligible. It's really essentially nothing if you were to compress them down and remove all the space in between them. So, in comparison to the volume that a gas actually occupies, the matter itself occupies versus the space that they're allowed to move around in is really not that much of a difference. It's very small. We also assume that the attractive and repulsive forces between the gas molecules are negligible. They effectively don't exist. It's not 100% true. They really only don't exist under certain conditions when the pressure is very low and the temperature is extremely high. Not exactly your normal conditions. So let's take a look over here about what's happening within the gas, sample of a gas. Energy is transferred between molecules. We usually say there's elastic collisions are perfect, and that's essentially true when we talk about a sample size, like an entire sample size. And while one molecule can actually bang into another and transfer and lose energy, the average kinetic energy doesn't actually change within time among a gas. This is assuming, of course, that the temperature of a gas remains constant. So what do we see? We happen to see a distribution curve within gases. Some of the molecules may be moving very slow. Others may be moving very fast, but most of them are moving close enough to the average speed of the gas itself. This graph is proportional to the temperature. For example, if you have a very hot gas, you're going to have a temperature curve, sorry, not temperature curve, a fraction curve that's a little bit lower because more of the gas molecules are going to be located having a higher speed. And that's really all temperature is simply how fast some molecules are moving. If you have a sample of a gas with an overall lower temperature, it peaks a little bit higher, but farther to the left because more of the gas molecules have a lower temperature speed. And then there's the behavior of the gases themselves. Effusion is one that not many students are initially familiar with, but they do see this on an everyday basis. This is the escape of gas molecules through a tiny little hole into an evacuated space. Because gas molecules are moving quickly, randomly, and constantly, they're going to find any tiny little hole, crack, or anything that they can possibly squeeze their way through. We often see this when a balloon, for example, deflates. It looks like the balloon is close to us, but gradually over time, through the pores of the latex, the small gas molecules are able to escape their way out. Now, effusion doesn't behave the same between gas molecules. In this example here, we see helium effusing at a faster rate because helium atoms are very small and very light. They're able to fit through the pores of the latex much easier. Argon is a significantly heavier gas. We can see that in the picture here by the fact that the argon balloon is actually heavier than air. But it doesn't seem to deflate. It's not actually getting significantly smaller in comparison to the helium balloon. A few argon atoms are able to escape, but not as many as a helium due to their size. And then there's one that you're more familiar with, the process and concept of diffusion. This is the spread of a substance throughout a space or throughout a second substance. Gases will diffuse throughout a room or other gas molecules randomly. The overall distance traveled is completely random because gas molecule movement is random. In the grossest example I can ever think of is someone happens to pass gas in a room, it will gradually diffuse throughout the room. It's going to be strongest and smell the worst right at the location that it entered the room, but over time it will spread out to the rest of the room, and that is kind of a gross thought to think about. Now, there is a formula that is technically used for effusion and diffusion, and it's called Graham's law, and it is really an HL topic, so we're only going to briefly look at this, although you will not be responsible for this. In Graham's law, we're actually comparing the rate of effusion or diffusion in one gas to another, and it is based off of their kinetic energy. In the end, Graham's law is really 1/2 times the mass times the velocity squared equals the other 1/2 m2v2 squared. This again is a comparison between two gases and their overall velocity. As we come to an end with gases, we should recognize that the ideal gas law is only going to occur under very specific conditions, and it makes the assumption that there are no intermolecular forces attracting the gases to one another. In reality, that's not always true. In reality, the gases are not at extremely high temperatures or very, very low pressures. In reality, that's almost impossible to achieve, and so the gases do not behave ideally. We often see some very, very crazy behaviors when the gases themselves are under high pressure and different temperatures. This makes the gases a tiny bit unpredictable. They will deviate a little bit from what we expect them to do. All of the assumptions of the kinetic molecular model break down at high temperatures or low temperatures. They simply behave a little bit differently. So, what do we do to correct this? Well, we actually have a method, but it depends on each individual gas. We can correct these minor changes here by using something known as a van der Waals equation. This is another HL topic and one that you will not be directly responsible for, but it is nice to know that there is a way to correct for non-ideal behavior. Unfortunately, that correction is quite literally dependent on what the gas is. The van der Waals equation is a modification of the ideal gas equation. You can actually see a little bit in there. Look, pressure, volume, and nRT. But then we add in a few other variables. For example, we add in constants, A and B, liters per mole or liters squared atmospheres mole squared. And each of these constants is different for every single gas. So the equation can be corrected as long as you know exactly what gas you work with and you have the van der Waals constants for those gases themselves. And if you recall from a previous unit, the intermolecular forces themselves were often called van der Waals forces. This is a recognition that it is the van der Waals forces that are causing these gases to behave non-ideally.